This is Dr. Carroll. Today's video is about the efficiency of tree operations. Okay, to get started, let's talk about retrieval, probably the easiest. So as a reminder, what retrieval does is it finds a node along a path from the root to a leaf, and it's going to terminate at a leaf in the worst case. So looking at an example here, if we're searching for something, we're going to start at the root and then we're going to proceed down until we either found the object or we hit a leaf. For example, if we're going to look for wheat, start at pasta, we hit wheat, we found it. If we're going to look for honey, we start at pasta, go to flour, go to oats, see that its left child is empty, and then we know we terminated. Okay? And so the big O for retrieval for a binary search tree is based on the height of the tree. You could also think of it as the length of the path from the root to the leaf. So we're going to be very focused on the height of the tree for this discussion. So that brings up a question. What type of binary tree will give a minimum height tree? What type of tree would give a minimum height tree? Well, the minimum would mean that we've packed in the nodes as much as possible per the height. And so we've completely or fully packed them in. And that's going to be the minimum height tree. It's a complete tree. And if to be truly minimum, for the least amount of height for the maximum number of nodes is going to be a full tree. Okay, well, that's the minimum height tree. So what type of binary tree will give a maximum height? Okay, well, let's go back to this example here. We've got our food tree here. What if we sorted these and put them in order? Meaning, what if we inserted beans and then flour and then oats and then pasta and then sugar and then wheat? What would that look like? It'd look like this. And what does that look like? Actually looks like a linked list. We need to be careful that our binary search tree implementation doesn't become an expensive linked list implementation. This is very possible. Is this a binary search tree? Yeah, it's a binary search tree. Is it a binary tree? Of course, because of that. Is it balanced? No, it's as unbalanced as you can get. Okay, so a maximum height tree is going to be with nodes in sorted order. Okay? So follow-up questions. For a binary tree with n nodes, what's the minimum height then? Okay, let's explore this a little bit. So here we have this little spreadsheet, and here we have two graphs. We're going to see the x-axis on this. The upper graph is the tree height, and the y-axis is the number of nodes. And this is for full binary trees. We're going to explore this because that's the maximum, that's the best case. And then here I've just changed the axes to make it a little bit more readable. So if we have a tree of height 1, we can have at most one node in there. As we increase the height of the tree, we're going to double the number of nodes that are in the previous level. And then this is the sum of all previous levels. Okay, so we've started our graph now. Now, go up to height 3. There's going to be 4 nodes in the last level. And that's going to give us a total of 7. We extend this. We're going to add 8, total of 15. Add 16. Add 32 for a total of 63. Starting to see a pattern here. That the total number of nodes in a tree looks very close to power of 2. If we go down to 10 here, we're going to get shapes like this. As the tree height goes up, we're doubling the number of nodes, doubling the number of nodes, doubling the number of nodes. So let's plot that differently. What if we have n plotted here? How does the tree height increase? How does the depth of the tree increase? Because that's what we're really focused on with the big O. Well, what does this graph look like? As n gets large, we go up just a little bit. Well, it looks a lot like log base 2. So here's log base 2 for the column C there, which is the number of nodes in a full tree, and it's rounded a little bit. It's rounded up just a little bit, but as you can see, compare log base 2 of n to the height. Okay, very close, fairly close, fairly close. It's just a little bit under the height of the tree. And then here it's close enough that rounding gets it. And we go up 1, go up by 1, go up by 1, go up by 1. And so if we were to graph log of n, it would go right over that. Okay? And that's an important concept, that the tree height for a minimum tree is pretty close to log base 2 of n. For a binary tree with n nodes, what's the maximum height going to be? Well, as we saw with this example here, it's going to be n. The height of the tree is going to be equal to the number of nodes. So the tree height is going to equal n. So that's for retrieval. That's the efficiency for retrieval then. Now let's talk about insertion. So in summary, what does insertion do? It finds where a node should go, and by finding it, it starts at the root, and it's going to make a path down to the leaf, and then it's going to insert it. Well, that sounds a lot like what retrieval is going to do. And so its big O is going to be the same as retrieval. Okay, now let's talk about deletion. What does it do? It finds a node, and then it deletes it. Well, if it has no children, it's done. If it has one child, it just moves it up, a simple operation, order 1. If it has 2 children, then what we're going to do is we're going to continue searching down the path until we, from the same path, root to leaf, until we find the in-order successor. So what it's going to do is it's still going to traverse that path from root to leaf. So its big O is going to be the same as retrieval, because it's still traversing the height of the tree is what the big O is going to be based on. So traversal then, our pre-order, in-order, or post-order, doesn't matter. What is it going to do? It's going to visit every node, which makes it pretty easy to calculate the big O then. So let's talk about the big O. So average case, let's start there, for retrieval is that going to be close to a full binary tree. Now it's not going to be really that, but it's close enough, and the details are beyond the scope of this video and course. And so we're just going to say that the average case is about log n. Okay? And we said insertion was just like retrieval in terms of it's going to scale the depth of the tree. For deletion, same thing. It's going to go through the entire depth of the tree, or the height. But for traversal, remember, it visits every node, so it's going to be order n. Now let's talk about worst case. For retrieval, the worst case is we've got this situation right here, and so it's going to be order n. And we said insertion is just like retrieval, and deletion is just like retrieval, that it's going to be order n on average. Traversal, again, is going to be order n. And that completes our video for today.